Welcome to Physics Training. So, welcome all of you. Warm greetings. Today we are going to see interesting topic, the next chapter of class 12 physics, that is dual nature of radiation and matter. Okay. So, we have seen so far all the Maxwell's equations of electromagnetism, Hertz experiments on the generation and reduction of electromagnetic waves in 1887. It is given in your book. So all these we have gone through, and then after that, during 1895 and all, there are more discoveries happens. So these are all based on what is an electromagnetic wave. Everyone knows. You know, the atoms absorbs, how the atom can absorb the outermost electron in an atom. Okay, so we used to call an atom is in ground state. Its energy level will be E1. Its energy level means we are just focusing the outermost electron or outermost valence shell. Okay, so the number of electrons in the outermost shell we are considering. So that electrons are trying to tend, or it tends to configurate in their stability. So that stability everyone knows after configuration. In order to maintain its stability, every atom tends to keep 8 electrons in its outermost orbit. In order to attain that, an atom has the tendency to lose electron or gain electron. This is the known fact. Okay. So if, for example, initially we used to call the energy levels as Bohr's postulates. Everything you just may recall all from Rutherford, J.J. Thomson to Bohr's. So Bohr's postulates convince that this E1 is nothing but it is the ground state of energy level. Each and every orbit is considered to be the energy shells or energy levels of an atom. For example, in each and every orbit, electrons are revolving around it. Okay, if electrons are revolving around it, then the electrons has its own kinetic energy due to the virtue of its motion. So that this kinetic energy, we used to call this as energy level. Based on the number of electrons present in the first orbit, the energy level is. Second orbit, there are 8 number of electrons, so energy level is high. Third orbit, 18 number of electrons, based on the maximum number of electrons. You know, right? All these rules, Hund's rule, Avga principle, then what is that? Pauli's exclusion principle. All these based on all the rules, the electrons originated in an increasing level of atomic structure. So increasing level of energy shells or orbits, if the electrons are filled in. Similarly, there are maximum number of electrons in each and every orbit, that's 2n square. So 2, 8, 18, 32, it goes on like that. So the energy levels are high when compared to the increasing level. Okay. See, for example, here what I am trying to figure out. Here, this lesson it deals with the dual nature of radiation and matter. So we have been so far gone through this particular area, or we know that the electromagnetic waves are nothing but it is a radiation, okay, coming out of an atom. How this radiation is possible? So you all knows, I've already taught you, children. So again, once again, I will teach you like this. So this is an energy level. So the first energy level, or it is said to be the ground level. Now what will happen? The outermost electrons, it absorbs energy from the sunlight, additional energies, okay, from the outsource, from the source, and then it won't stay in its level. So that it moves on to the higher energy level. It jumps to the higher energy level where it can occupy. So there also, so that energy level are said to be the excited level. So this is an excited level. Okay, this is ground level. Okay, so this excited level and ground levels are very important for an object or for an atom, for example. So the outermost electrons or outermost orbital electrons, it absorbs energy from the source, especially from the sunlight. Then what will happen? It moves to the higher excited state. Here also it has its own limited time period. So it did not lie in this particular excited level for a long hours. Okay. So it will stay here not permanently, it is temporary here. So very limited period of time it may stay here, and then it comes back to its original position or ground state by releasing energy, unless otherwise it can't able to come. Okay, for example, the first ground state energy level is 13.6 electron volt. Here, for example, 72 electron volt. It has to lose this much of, 72 minus 13.6 electron volt has to be reduced. Okay, near about. So, near about 68.4 electron volt is removed. This amount of energy has to be released by an electron, those electrons. So, now it tends to come to the ground state by releasing energy. So, this energy is in the form of radiation, or this is usually we used to call, since the electrons are involved, as I told you already, we have been so far learned all the electric field and the magnetic field and how the electron is associated with both electric and magnetic field. Okay, so if the electron is losing some radiation, okay, then what will happen? It is combined electric and magnetic waves. So electromagnetic radiations are coming out in the form of waves. Okay, so for example here, EM waves. So there are so many things you can able to observe. So there are metastable state also. Suppose not all the electrons emit radiation and it moves back to its ground level. It may reach some metastable state, and after that, so this is after that it has to be stimulated by some other source. After stimulation, it goes to the ground state. This will also happens. Okay. So laser radiation and everything is a very great example. Okay. So you just go through all these things. It is very important. With this idea, we are going to get into this chapter. So atom has its own property. Okay. So it is now radiating energy. Okay. So this electromagnetic radiation is in the form of waves I am seeing. Okay. So if there is a wave, definitely there should be a particle, unless otherwise there is not wave. Okay, understood. So if there is a wave, means particle has to be there. If there is particle exhibit, so that exhibits a wave. So both a particle as well as a wave. So this is the dual nature of this particular atom. So dual nature can be clearly explained, okay, in the upcoming lesson. So in your chapter, I am going to project your chapter here. So okay, so all the you have to understand all the theories. So you have studied completely in the structure of atoms. Yeah, in class 11 chemistry. Okay, so all the NCERT board students, you can learn all these structure of atoms in chemistry. You better go through that right from J.J. Thomson, Rutherford, and then Millikan's experiments. Every experiment you have seen. For JEE mains and all, I think the JEE mains children you have applied. Okay, so most of the children. So there is one more column, one more addition must be there in that. You might have seen the experimental studies. So you have to include all these things. You must know what is the experiment about. Okay. So now before getting to this, we must know what is going on and what all the emissions are there. Okay. So in your book it is given there is electron emission. Okay. So that emission, how the electron is emitted. Okay. In what way the electron can be emitted. Okay. So that is we are going to learn right now. So once of all, you have to understand what is 1 electron volt. 1 electron volt is converted into joules. Okay, it is equal to 1.602 into 10 to the power of minus 19 joules. So this is the energy equivalent. Now we are going to learn how the electron is emitted here. Let me show you. So photoelectric emission. Everyone knows Albert Einstein. He is the one who has created a lot of impact. So Albert Einstein, he, along with Planck, he suggested there is an electron. So this electron has its own mass. It is just emitting frequency, it is emitting radiation, as we have seen so far, right? How the radiation is emitted. Since the wave is connected, means the wave is, suppose for example, you are considering an electromagnetic wave, right? If there is an electromagnetic wave, this electromagnetic wave has its own wavelength. You know, any successive crust or curve, it should have wavelength. The distance between, okay, it is wavelength. It is measured in meter, and then the number of waves per, 1 second. So this is number of waves. What is the frequency? Frequency is denoted by letter nu or n, whatever it might be. So the number of waves per second. What is frequency? Number of waves per second. So this is frequency. So all about. Then you must come across here. How we are taking electron, okay? So in a particular structure of atom, you are just seeing that electromagnetic wave radiation is there, okay? So how the electromagnetic radiation is there? For example, what is there? I told you no. So this is Planck's radiation energy. So you know all these things. E is equal to h nu is nothing but it is the Planck's energy model. So Planck considered a quanta of atoms, quanta of particles. Quanta means a small amount of particles. Okay. So he considered not a single particle. He considered an amount of particles. Okay. So for that, the number of frequencies, number of radiations, number of waves per second is said to be this nu, this frequency. H is the Planck's constant. Since based on Einstein's theory, Planck derived this energy radiation formula. Okay, this is very important. Everybody knows E is equal to mc square. That is Einstein's energy formula. So energy is related to. Suppose if you are considering electron has its own mass, and then if we all come across now, so what is an electromagnetic waves, electromagnetic spectrum. So everything you have learned in your class 12 chapter, last chapter, electromagnetic waves, as well as you have learned structure of atoms also. Structure of atoms in chemistry, okay, class 11 chemistry. So you know all these things. C is nothing but the speed of light. Because we can see only the visible region of an electromagnetic waves, reminding ultraviolet rays, infrared rays, microwaves, radio waves, so many things are there. Okay, so but we come across, we can able to see the visible region, so that we are focusing the light. Okay, so the frequency of the light or the speed of a light. Here we are taking the frequency or speed of a light. So all may know what is that actually. The light is emitted. Okay. So this is what it is happening here. So E is equal to mc square can be equated to E is equal to h nu. Both can be compared by de Broglie. Now we are going to see that relation also. So based on that, de Broglie suggested there is a dual nature of a light. Okay. So there is a dual nature of a particle. So a particle can behave both particle as well as a wave. That is his argument. So he compared E is equal to mc square and E is equal to h nu. Okay. So now we are going to look after this thing. So what it says. Now this is an electron. a light is exposed on an electron, right? For example here, so a light is exposed on an electron. So this is known as a photon. Light particle is known as a photon. Okay. Now photon is absorbed by this particular electron. Get my point, all of you? Okay. Then, so let us watch over this. See here, I have explained you what is quanta. Quanta means a small amount. Okay. So what is the E photon? The energy of a photon also H nu, right? So H nu is the energy of H is Planck's constant, everybody knows. Nu is the frequency of a light. Since we can able to see only the visible region, so it is said to be light. Okay. Then what happens here when the photon is targeted on this particular atomic structure? Electron absorbs energy. So what it says here, for example, watch over this. See here. Okay. So light is incident on it. So electron absorbs energy to overcome the work function. This is what we are going to learn from this work function. Okay. So what is the work function? It is denoted by letter phi naught in your book. Okay. So work function is nothing but it has to work. It has to work to overcome. It has to work something. So what is the work? So electron absorbs energy. So in order to maintain the conservation of energy, the energy should not be lost by it, right? It should be converted into some useful work. So that is said to be the work function. We usually denote this work function as a letter phi naught. Now, what happens? So kinetic energy of emitted electron. Now the electron is emitted, right? So that is said to be K max. So unless otherwise, if it doesn't achieve that maximum kinetic energy, it won't be emitted. Okay, this is very important when the photon is incident on a particular material. So we are just exaggerating everything here. Okay, so you are targeting on metal. Okay, metal target is there, metal sheet or metal plate, for example. So here we are considering some atomic structure here. We are considering one atomic structure. There is one electron inside. Okay, for example, suppose that electron is now emitted out of the metal. So how it is emitted from the surface? So it is emitted by hitting a photon on its surface. So the photon energy helps the electron to absorb more energy. These electrons absorb more energy to overcome the work function. Okay, so to overcome the work function means the result is the electron is producing actually what we can say it is just escaped from the metal. It is just emitted from the metal. So that we can come to know the electron normally it is having kinetic energy. Now it achieves maximum kinetic energy by the absorption of photons. Okay, by the absorption of photons. Now the light is incident on the metal target, right? So this is the matter. Here, that kinetic kinetic energy maximum is H nu minus phi naught. Okay, so so the initial energy you know that is H nu. Okay, phi naught is the work function. The electron has to overcome the work function so that what is the remaining energy that is said to be the kinetic energy maximum. Understood? So this idea you should get first. Then only we can come into the lesson. So next, yeah. So intensity of incident radiation is increased if suppose this is incident radiation. Light is incident on it. This is incident radiation. You might have seen some light path, right? So this is the beam of light. So if the intensity of incident radiation is increased, then what will happen? Number of emitted electrons per second also increases, right? So it absorbs more and more energy, so that number of electron emitted also increased. Okay. Listen carefully. You have to take a note of all these things, each and every point, since it's theory. Okay, so you have to take a note of each and every point. So this is very important. Children, learn along with me, so that it is useful for your board exams. So now kinetic mass is written as h nu minus phi naught. So kinetic energy depends on frequency, right? So here, just watch it. What is kinetic energy? It depends on mu, frequency. Okay? And then kinetic energy does not depend on the intensity of radiation. This is very important. See, for example, intensity of incident radiation is increased, number of emitted electrons per second increases, but not the kinetic energy. So the maximum kinetic energy of an electron does not depend upon the intensity of an incident radiation. This is very important point. It depends only on the frequency of an incident radiation. Okay, only upon the frequency, does not depend on intensity of radiation. Listen carefully. Kinetic mass will be non-negative. Always. Unless otherwise, it can't, if it is negative, then it can't overcome the work function. If it is overcoming the work function, then only it can be able to emit it from the metal target. Okay? So it is always positive. If it is positive, the photoelectric emission should be, if it is positive, then for example, see here, it is always positive we are taking. So that we can take, it is greater than 0, right? H mu minus phi naught, H mu minus phi naught is always positive. So that we can take H nu, you can bring this phi naught here, is always greater than the work function. So this is very important. Okay. What is this mu or mu naught? Mu and mu naught will be, mu naught is the initial frequency. This mu is the final frequency when it is absorbed, when it absorbs all the incident radiation. After absorbing all the incident light, the radiation will be, the frequency will be mu. Okay, mu is now greater than mu naught. This is original frequency. See, for example, what it is insisting, this equation, keep in your mind. Yeah. If it is greater than mu naught, that is equal to phi naught by h. What is that phi naught by h? You have to come across. What is the initial one? H mu naught minus phi naught. That is equal to 0. For example, we are taking. Then h mu naught is equal to phi naught. Then mu naught is equal to phi naught by h. So that is what it is given. Mu naught is equal to phi naught by h. If the work function is high, threshold frequency is also high. What is the threshold frequency? That is the frequency where the radiation is started. For example, okay, where the electron emission is started. From that frequency only, the electron emission started. That is the frequency before, okay, before the emission. So at that frequency, at the threshold frequency, that is mu naught, it is said to be. From that only the emission started. So it is actually the work function phi naught is high means it is depending upon what it depends upon, phi naught by h. H is Planck's constant. So that is equal to threshold frequency. It is directly proportional to threshold frequency. So what is that? It is also high. So threshold frequency mu naught exists in the absence of photoelectric emission. So what is the meaning? So photoelectric emission means the photons are incident on this particular metal target, for example. You are seeing, right? So these are all the photons. So these particles, you might have seen these are all the photons. The photons are just incident on this metal target. Okay? So not suddenly the electron emission takes place. The electron emission takes place after it achieves threshold frequency. So what we said here, threshold frequency exists in the absence of photoelectric emission. Understood? So by achieving that, after that only the emission takes place. Okay? So let us move on. Then you know that intensity of radiation, that is equal to number of energy, then unit area, that is intensity, or unit time. Okay, per unit area, per unit time, that is intensity. So greater the number of quanta means you know the amount of particles, the amount of energy. Greater is the number of electrons absorbing quanta, right? So, yeah, I will come to this point. Greater the number of quanta, greater is the number of electrons absorbing quanta, right? So that the greater the emission will be, electron emission will be. Greater the number of electrons coming out of the metal. Okay? Then photoelectric current. You know that? You know that if there is an emission of electron, definitely due to the flow of electron, there is a current. So that is said to be the photoelectric current. So photoelectric current also directly proportional to the intensity of radiation. See, this is an experimental setup. You must understand it is photoelectric emission. Okay? Now, clearly it shows the light is emitted, light is incident on it. Based on this light radiation, the electron is emitted here. So, a metal target is here, for example, we have taken this. So, a metal target is now, a light is incident on this metal target, so that electron is emitted from here. So, this is what we have observed so far. So, there are so many parameters involved. There are so many terms we have studied, which will be, what and all dependent. So, that is very important. Okay. So, you just take a note of each and everything. Suppose if you want to know more, you can rewind and then you just watch it again and again. Keep your book along with you. So based on that, you can just view our video lesson so that you can parallel with your book and the video lesson. It's very easy to understand. So current, there is a photocurrent we studied. So photocurrent is directly, it is mentioned as microampere. There is a voltage also. If there is a photocurrent, there is a voltage, right? Go through this again. Intensity determines number of electrons. It produces number of electrons, produces photoelectric current. This is what here you have to understand. Okay. So this is a variable resistance here. Okay. Voltmeter to measure the voltage. So here it is an ammeter. It is measured a current, photoelectric current in microamps. Okay. This is a commutator, keyser actually. Okay. It is connected to anode and cathode here. Okay. So this cathode metal target is now just a light is incident on it. So what is the Kmax? Kmax is equal to, we measure that in electron volt. Okay? E into V naught. So what is this E V naught? That is equal to hν minus phi naught. Okay? So hν minus phi naught is nothing but here you know that E V naught is the kinetic energy maximum, right? Electron volt. So here, what is this V naught and phi naught and mu naught? Everything you know. That is the that is actually the frequency, the kinetic energy before the emission of electrons. Okay, that is the work function also. Phi naught is. You know that it can be equated right now. In order to know, we know that what is actually the conservation of energy. What is conservation of energy? Kinetic energy before the emission of photoelectron should be equal to the kinetic energy after the emission of photoelectron. So suppose if there is energy lost or energy gained, so that should be converted into useful work. So this is the theory. Unless otherwise it may violate the law, right? So law of conservation should be there. So here, in order to prove the law of conservation of energy, here before emission and after emission, the kinetic energy maximum is equated. Okay? We know that nu is greater than or equal to nu naught. So now, don't confuse with nu as velocity. Nu is the frequency. Okay. So what is nu naught now? V naught now. You can divide h by E into nu minus phi naught by E. You can divide this E, right? That is V naught. Okay? That's all. This thing you have to take a note of all these things. With this we are going to learn so many experiments. I will teach you from your book. I will teach you from your book. We will move on to the book actually. So this is dual nature of matter. I think it's visible to you all. Is it visible all of you? Okay. So these are all we have already gone through it, experimental setup, everything. Okay, I have shown through some simulations. Just go through it. You know the intensity of light and the photoelectric current. We saw both are directly proportional, right? Photoelectric current is proportional to intensity of light. Suppose if it is proportional, then it should be shown in increasing slope. That is a straight line. So we have learned all these things, effect of intensity of light on photocurrent, potential on photocurrent. So this is intensity of light on photocurrent. So this is potential. So this is nothing but, you just go through this and explain it. Okay, this is what we have seen. This is the maximum kinetic energy. Based on the stopping potential, we have learned V naught, right? What is the stopping potential? I'll explain you. Okay. See, for example, it is found that the photoelectric current increases with increase in positive. One second. So it is increases. Which one is increasing? Actually, the positive potential of plate A gradually and measure the resulting photocurrent each time. So it is found that the photocurrent increases with increase in positive potential. If the potential increases positively, this is positive current, photocurrent, this is positive potential. So that is collector plate potential. You don't know about all these things, collector, emitter and base. Okay, these are all the transistor we can talk about, semiconductor devices. So, okay, so here you just keep in your mind. So if the positive potential is there, you might have seen, what is that? Photoelectric current increases. So photoelectric current increases. Okay? It is found that the photoelectric current increases with increase in positive potential. So this is the graph it conveys. Okay? Then at some stage, for a certain positive potential of plate A, all the emitted electrons are collected by the plate A and the photoelectric current becomes maximum or saturates. Okay? So there are some stages. What is the certain stage actually? Some saturation might be there. It is keep on increasing and then it is saturated for some reason. Okay? So it is saturated or collected in the collected plate. That means it is, photoelectric current is collected means the emission of electron is there. Okay? Then, okay, if we increase the accelerating potential of plate A further, the photoelectric current does not increase. Again you are increasing further. After reaching the positive V naught, again you are increasing further, then increase, keep on increasing. There is no increase of this particular photoelectric current. The current is saturated. Okay. So that type of current is known as saturation current. So saturation current corresponds to the case when all the photoelectrons emitted by the emitter plate C reaches the collector plate. Okay. So what is the confirmation mark? So there is an emitter collector. As I told you, it is nothing but it is a transistor. It is not in your syllabus. Actually, it is a semiconductor device. Okay, like this it will be. It is a semiconductor device. Like this. So the base is grounded. Base is grounded here. Here it is emitter. Here it is collector. Like input and output. Like. It is a transistor symbol I am saying. Say for example, what they said, there is a saturation current. Saturation current means it is the fullness of current. If the current is saturated, if we keep on increasing the potential, then we come to know all the electrons are collected at the collector plate. Okay? So that is what they are trying to say. So we now apply a negative potential to the plate. So this is also known as retarding. Positive potential also known as accelerating potential. Okay. So plate A with respect to the plate C, and then I'll make it increasingly negative. Okay, so here they said, so if you have keep on increasing negatively, you are just increasing negatively here. Then what will happen? See, when the polarity is reversed, the electrons are repelled and only the sufficient energetic electrons are able to reach the collector A. Not all the electrons, only the sufficient electrons are able to reach the collector. Okay. So in the collector plate, the electron is now reversed, right? While you are increasing the potential, now the electron is driven away in one direction. Now the potential is now reversed in negative manner. So electron also reversing. Understood? This is what it says. The photocurrent is found to decrease rapidly until it drops to zero. Like this. The current is decreasing, keep on decreasing. Okay? So during positive potential, what will happen? It is gradually increasing. So increasing for some reasons and then it again saturated if you keep on increasing the potential. But if you reverse the potential, that is the potential is negative, the retarding potential is there, then the current keep on decreasing. Gradually it is decreasing and reaches to zero level. Okay? That potential is said to be the retarding potential or stopping potential, where it stops the movement of the electron. So it is known as stopping potential. The photocurrent is found to decrease rapidly until it drops to zero. It is certain sharply defined. The critical value of the negative potential V0. Okay, this is known as the negative potential or retarding potential V0. So at which the photocurrent stops or becomes zero. It is called the stopping potential. Okay, so it is given here. Okay. So from this we come to know all the photoelectrons emitted from the metal do not have the same energy. This is very important. Okay. So we do not come to know all the electrons emitted from all the electrons should have the same energy. Okay, emitted from the metal. Okay. So photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons. Okay. So we saw the kinetic mass that is equal to EV0, right? So this is what, from this only we are just going to see. Here there is no emission of electrons. Okay. So we can now repeat this experiment with incident radiation of the same frequency but of higher intensity I2, I2. Like this we can be able to repeat this experiment. For first I1, here I2, I2. So this is, we have repeated for various currents, right? We have repeated. Then, okay. So what is the stopping potential? It remains the same for all different kinds of intensity of radiation. Okay, but the stopping potential remains same. Okay? Is it clear for you? In other words, the maximum kinetic energy of photoelectrons depends on the light source and the emitter plate material. Okay? This is very important. What it depends upon the kinetic energy of photoelectrons? It depends upon the light source. Okay? And the emitter plate material. That is input, I am saying. But it is independent of intensity of incident radiation. Intensity is independent to that. So, but intensity is directly proportional to what? What we saw actually already. Okay? What we saw? Photoelectric current is directly proportional to the intensity of light. Current is directly proportional to the intensity of light, but not the number of electrons emitted. We can say number of electrons emitted also, but not the frequency. Okay? So the frequency is nothing but what we said, the maximum kinetic energy of this point is again and again insisted in your chapter. I have given you earlier based on the simulation. Kinetic energy maximum does not depend upon the intensity of radiation. Okay, intensity of radiation directly proportional to the photoelectric current only, not the kinetic max. Okay, photoelectric current means directly depends upon the emission of electrons also. Based on that only current comes. So this is the effect of frequency of incident radiation on stopping potential. See here various stopping potential we are taking. Okay, what is the frequency? So that is what given here. So this is first stopping potential, second stopping potential, third stopping potential. Based on that, the frequency varies. See here. Then at one point of potential, all matches and then it follows. Then that is saturated right now. So frequency is varying for each of their free retarding potential, various retarding potential, and then that frequency at one point of potential, positive potential, it reaches the saturation. So that is constant after that. So this is what here shows. Okay. So what the graph shows here. In the previous one, you saw based on the stopping potential, x-axis, that is the potential. In the y-axis, photoelectric current. Okay, this is the varying current, different levels of current. Here, the frequency is varied. Okay, so only difference is that. See, the graph shows that the stopping potential V naught varies linearly with frequency of incident radiation for a given photosensitive material. See here, it linearly varies. For example, here. Okay, there exists a certain maximum cutoff frequency. This is maximum cutoff frequency for which the stopping potential is 0. So they said, okay, stopping potential is 0. Here and now stopping potential is there. So after that stopping potential is 0. Then these observations have two implications. What are the two implications? The maximum kinetic energy of the photoelectron varies linearly with the frequency of this and all we have seen already. Frequency of incident radiation, but it is independent of its intensity. That's what I've told you already. So for frequency nu of incident radiation, lower than the cutoff frequency nu naught, no photoelectric emission is possible even if the intensity is not. This and all we have seen already. All these points. We just go through it. Okay? So photoelectric effect and wave theory of light, now we are going to see. So this also I have explained how the emission takes place. Due to that emission, that electromagnetic wave electromagnetic radiation is emitted, so that is wave. Right? If that is a wave, that is a particle. So particle exhibits a wave. So both particle as well as a wave. Okay, so we are just going to interpret. So this only we saw Einstein's photoelectric equation, energy quantum of radiation. We saw through this. Everything we have discussed. Just go through in your book. So I have told you all these things. I will explain you the de Broglie's wave equation. So this thing also I will explain you. Here they have explained what is it actually. E is equal to h nu, we know, right? Each photon has energy, E is equal to h nu. What is the momentum? Momentum is equal to mass times velocity, right? Mass times velocity, that can be equated to like this. So what is mass times velocity? So velocity is equal to distance by time, everybody knows. So if there is a velocity of a particle, light velocity or the velocity of a photon, we usually denote it by letter c. And then distance, since it is a wave, we can usually denote the letter lambda. Then the time, 1 by time period can be considered as the frequency. What is 1 by time? It is frequency. So c is equal to lambda f also we can write, or c is equal to lambda nu also we can write. C is equal to nu lambda. So likewise we can equate. Okay. So this thing, it is not given clearly. I will explain you right now how the momentum and the energy is equated here. All of you take a note. I will explain you in a proper way. You know that what is Einstein's mass energy relations? Let me write here so that you can catch it up. E is equal to mc square is the Einstein's mass energy relation, and then E is equal to h nu. H nu is the Planck's relation for the quanta of energy. So we can equate, as I told you, we can equate these two. And then from this the momentum can be calculated. If you multiply and divide by m, then this is known as momentum. So momentum is equal to mass times velocity. Since c is the velocity of light, okay, so we can write. So m square c square by m, that is equal to h into nu. And then what is m square c square? That is equal to v square by m, h nu. Understood? So as I have told you, what is this nu, what is this p square and everything. So we can just calculate what is nu. Okay, nu can be written as c is equal to nu lambda. From this formula, nu can be written as c by lambda. So you can equate. So mass can be eradicated here. We can do like the same. Unless otherwise, that is one way. Take a note. E is equal to mc square. We can just eliminate mass by mathematical calculation. So mc square is equal to h nu. Okay. So mc square can be written as hc by lambda. Nu can be written as hc by lambda. So one c we can cancel here. Okay. So that is m into c. That is equal to h by lambda. What is m into c? This is momentum. It's equal to h by lambda. Or lambda is equal to h by v. We can equate these two. So this is the famous relation. So that is what given here. P is equal to h by lambda. Right? So take a note of this. This is very important. So based on this problem is dealt. Okay, it is dealt with. What is that? Monochromatic light of frequency. This is produced by a laser. So as I have told you, that ground level and excited level. So that amount, we come to know about there is a metastable state also. Then from that, you just have a stimulation. Then by stimulating it, then it is just coming back to its original state. So if it is coming back to its original state, it emits a monochromatic light. So a laser is a highly monochromatic beam. Okay, it is having single wavelength. And then sharp and intense also. So monochromatic light of frequency 6 into 10 to the power 14 hertz is produced by laser. So it is frequency given as hertz. Then the power emitted is given as 2 times 10 power minus 3 watts. It is 2 times 10 power minus 3 watts. What is the energy of a photon in the light beam? So this is the question asked. how many photons per second on average are emitted by the source? This is the second question. So each photon has an energy. What is the energy? E is equal to hν is an energy. Okay. So H is given here. Nu we know. What is nu? It is given here. H is Planck's constant, or always do remind in your mind this H is given as a hint. Okay, don't worry. Even then you should keep in your mind. So 6.63 into 10 to the power of minus 34 joule second. Multiply this. You can multiply the number and then again the expansions. I mean on the exponential. So this is joules. Actually hertz is nothing but second inverse. So second inverse and second gets cancelled. So result is joule. Okay. Joule can also be converted into electron volt by the conversion. What is 1 electron volt? 1 electron volt is equal to 1.602 into 10 to the power of minus 90 joules. You can suppose if you are asked to find an electron volt, you can convert that. What is 1 electron volt? 1.602 into 10 to the power of minus 90 joules. Okay. So then number of electrons, how many photons per second and an average are emitted by the source. So number of photons emitted by the source per second. So what is the number of photons? So P, the bar P is transmitted in the beam. Okay. And then it is equals to n times the energy per proton. What is the bar? N times the energy per proton. So bar is equal to n times the energy per photon. So per photon, that is n times it is equal to. So n times this. So what is n? N is the number of photons. So bar by energy is the number of photons. Okay. So this is 5 times 10 power 15 photons per second, because bar also given. 2 into 10 to the power of minus 3 watts. So do just calculate and then find out. And the next one, work function is given. Cesium atom. It is given. Find the threshold frequency for cesium. You know the formula, right? This is all we have learned. So substitute and find out. Very, very important. You have to, for division and all, 2.14 divided by 6.63. So first of all, 2.14 divided by 6.63 means you can just, both are in two decimal places. So you can remove the decimal places. That means you are dividing here by 100, here by 100. So those two gets cancelled. So you can just do like this. Okay. And then what else given here? So 214 is now divided by 663. So it won't go, so put decimal point, 0 point, and then again add 0. Here and all you have to just round off everything. Round off this 663 in your mind itself, I am saying. Round of 663 into 700. Round of 2140 as 2100. So you know that 700, when you divide this 2100 by 700, it is 3 times. So better multiply it 3 times. For guessing itself I am saying. So 3 3s are 9, then 6 3s are 18. Okay, reminder 1, then 6 3s are 18. So this might be the, okay, then 13, 8, 5 it will be, then 10, 9, sorry. So it will be like this. So reminder is 151. Again you just go through this. Okay. Again if you put 700 it will be 2 times. Okay. So 3 2s are 6, 12, reminder 1, 13. So likewise you just proceed. Understood? And then you should just bring this 10 power minus 34 to the top. Understood? Keep this in your mind. Then it is in electron volt, it should be converted into joules, because we know that H is always, unit of H is joule second. In order to match up with this is the SI unit. In order to match up with this, electron volt is now converted into joules. After finding that, you can just multiply with 1.6. So 10 power minus 19 and 10 power minus 34, it goes upstairs, then it will be plus 34 when it goes up. Okay. So this might be the answer. This is multiplication and all, it is very simple to you. Okay. Likewise, you just follow all the calculations. Calculations are very much important. You have to do practice all these calculations. Like this is how we come across. This is E V naught is the kinetic maximum. That is at the stopping potential. Where there is no emission of photoelectrons. After that only the photoelectron is emitted by overcoming the work function. Okay, so that is said to be h nu minus phi naught. So this is all you know. We equate and find out. So wave nature of matter. So he is de Broglie, the real great man. He found that the dual nature. He only suggested there is a dual nature of a particle. Okay, and then go through this. I have explained you this thing, right? Lambda is equal to h by p. So that is what given here. This is a famous relation. So based on this, a problem is discussed. So that's all the dual nature of matter in your book. It's very simple chapter, and then you just come across all these things. It's very important also. Okay. So you have already learned in your class 11 chemistry, structure of atoms, all these things. Okay. So maximum photo, all these theory, discovery of electrons, discovery of protons, neutrons, everything you have studied. Better go through this chapter also again. Okay. And then photoelectric emission also discussed in the class 11 chapter. See, particle nature of electromagnetic radiation. Planck's quantum theory is discussed here. So you better go through this again. Photoelectric effect, so that you may be getting questions from chemistry as well as physics also. For example, if you are going to write JEE mains, you can learn parallelly the class 11 atomic structure as well as this dual nature of matter. Okay, so it is helpful for you guys. Thank you.